Hey guys, I'd like to use this example problem to show you how to solve a typical projectile motion problem. In the question, it says a place kicker in the Canadian Football League is attempted to hit a 52-meter field goal to win a game. If the ball leaves his foot at 24 meters per second with an angle of 50 degrees from the ground, A, how far will the ball travel? And B, by how much will it clear the uprights, which stand 3 meters off the ground? So the first thing we're going to do anytime we're solving a problem is draw a picture. So in this case, you've got the ball leaving the ground and being kicked at an angle of 50 degrees with some velocity. So there's my 50-degree angle, and my initial velocity is always going to be the angled piece, which in this case is 24 meters per second, and it's at an angle of 50 degrees, and it's going to follow a parabolic trajectory all the way to the end. All right, and we would call that our x final. So right here is our initial position in the x. We'll call that 0 meters. And it's going to land somewhere here, which we don't know. That's what we're trying to find in part A. Now, if we have an axis set up, I'm going to have my x direction this way and my y direction that way, which means we're actually also at a y initial position of 0 meters and a y final position of also 0 meters at the end here. And that position is going to change depending on where you are along that trajectory. So in part A, we want how far it travels, so we're looking for when it's going to be on the ground again. So my initial position is right here, and my final position is at the end of the parabola on the ground again. So the next step we're going to do is set up an XY table, because this ball is going to be moving in the X direction horizontally and in the vertical direction simultaneously, and they act independent of each other. So in the X direction, we have an acceleration in the x, which is always going to be 0 meters per second squared, which simplifies our equations up above because the a goes away in the first equation, it goes away in this equation, and it goes away and takes that whole piece away, which means the second two equations, this one and this one, basically confirm what we already know, that the initial velocity is equal to the final velocity in the x direction, which leaves us our only equation in the x direction, which is a constant velocity equation. X final is v initial times t plus our initial position. So the x side is pretty easy. Sometimes I don't even put a x in there. You're going to have some time at which the ball is traveling. The velocity initial is equal to the velocity final, so I just call it vx. It's got a starting position and it's got a finishing position. In this case, it starts at 0 meters and it finishes somewhere downrange. Now be careful, it says 52-meter field goal. That's the distance to the field goal marker, which is going to be somewhere over here that it has to pass through. This position is going to be 52 meters at that point. So we're assuming it's going to make it through the uprights. So at that point, we're going to find our landing position after 52 meters is what we're hoping. So we don't know our final position. We have a velocity, but it's not directed in the x direction, so I don't know that yet. And we have a is equal to 0. Let's look at the y side. As it moves vertically, gravity is going to be the accelerator. So in the y direction, you have negative 9.8 meters per second squared. You're going to have a time at which it's traveling vertically. You're going to have an initial velocity in the y, which is the speed that it leaves vertically at the start. You're going to have a final velocity in the y, which is the speed it hits the ground vertically. You're going to have an initial position in the y, which is on the ground, and it's going to finish on the ground. So let's look at how we solve this problem from here. Now, we don't have enough information to get anything because we don't have our velocities in the x and y direction yet. So let's look at this launch velocity and break it down. Since that 24 meters per second is at an angle, we can't say it's in just the x or just the y. So what we need to do is resolve that into its pieces, its components that act in the x and y direction. So you have one piece which goes in the x direction, we call that vx, and you have another piece that's acting at the same time in the y direction. That would be the velocity initially in the y. And those meet at a right angle, And right now you don't see the triangle, but with vectors you can move them around and add them in any order. And if we're going to actually add the vectors, I would put the VIY over here. And you would see that you have a right angle between x and y, and you have a triangle with an angle of 50 degrees and a hypotenuse of 24 meters per second. And our trig, SOHCAHTOA, is our mnemonic, says that the sine of any angle theta is equal to the opposite over the hypotenuse, and the cosine of theta is equal to the adjacent over the hypotenuse. Well, in this case, we have the hypotenuse and we have the angle, and the opposite side would be VIY. And so VIY is equal to the hypotenuse times sine of theta, sine of 50 degrees. And in the x direction, you have 24 cosine of 50 degrees. And when you pull out your calculator, we need to make sure that we are in degree mode. If you look in mode, I'm in degrees, this third line, otherwise we'd have an issue. And I'm going to type in 24, the velocity, times sine of 50 degrees. And if I hit enter, I get 18.39 is the velocity in the y direction. So effectively what we're saying, when we throw this at 24 meters per second at 50 degrees above horizontal, it's no different than throwing a ball vertically at 18.39 meters per second up and down. That ball will go the same height and will be in the air just as long. And in the x direction, we have the same equation except with cosine. 15.43 is the velocity in the x, which says if I rolled that ball along the ground at 15.4 meters per second, it would reach the end at the same time that this kicked ball reaches the end. So now that we've described the velocities in just the x and the y direction, now we can fill in our table with those values. Our x component of the initial velocity is 15.43 meters per second, and the y component is 18.39 meters per second. So when I look on my left side, I need x final. That's the answer that I want for part A, and I'm missing time. Now, this ball is moving along that parabola, and the time in the x direction is equal to the time in the y. So what bridges our gap is this time component. So if I can find the time the ball's in the air, then I can then use that time in the x side to find the final position. So using my xy table, I'm going to find, in part 1, I'm going to find the time the ball's in the air. And we're going to use the y side of our table. And if you look at our equation, we have the initial velocity. We have our two positions. In this case, they're y positions, but we can use them the same. And we have our acceleration, which means I have everything except time. I can use the first equation to find the time. You could also, in a two-step problem, use the fact that we have the initial velocity, we have A, we have x final and x initial to find what v final is, and then plug that in here, here, and here to find time. What you also may notice is since this ball starts and finishes on the ground, what we've known in one-dimensional motion, this object should strike the ground with the same velocity in the y direction, but negative. So I can immediately put negative 18.39 meters per second right here as the final velocity. That is only going to be true when the position in the y initial, is equal to y final. And if I know that, I can go right to the second equation to solve for t. For the time being, let's stick with our first equation because this will work for any projectile problem. So I've got my equation, y final is 1/2 ay t squared plus the initial velocity in the y times t plus y initial. And I'm going to plug in what I have. I have 0 equals half of negative 9.8, which is negative 4.9 t squared, plus my initial velocity in the y, 18.39 t, plus my initial position. Now, what I've encouraged all you guys to do is use the quadratic formula and program it in your calculator. This would be my A term, this would be my B, and this would be my C. In this special case where our C term is 0, it simplifies the math. You can solve by factoring, but for the sake of time, I'm going to pull up my calculator, and in here I've already programmed the quadratic formula. When I hit enter, it's going to ask me for my A term, negative 4.9, my B term, 18.39, my C term is 0, and I'm going to get 2 times, a time of 0 and a time of 3.75. T equals 0 seconds and 3.75 seconds. I get 2 times because it's quadratic, and these are the 2 times at which the object is on the ground at a position of 0. Well, that occurred when it left the foot at time 0, and it occurred again when it hit the ground later. So I'm going to use this later time, and this now goes into my table. It's 3.75 seconds, and it bridges the gap to the other side because the ball is moving the X direction over the same time period. And so my second step would be to use the time in the air to get my final position. And again, my only equation, it's really the same equation I just used, except when A is 0, my equation in the X direction simplifies to the final position is equal to the velocity in the X times time plus the initial position. And I can plug in my velocity, 15.43, and multiply it by the time the ball is in the air, 3.75 plus 0. And I get a final position for this object, 3.75 times 15.43. This object is going to be 57.86 meters away. That's my answer for A.